Well, I guess with that, we'll get started here. All right, Michael?
Sounds good.
So first and foremost, a quick thank you to those joining us today. I know we're going to have a large audience, and just like a number of the other Zoom webinar and training sessions, we learned very quickly on in the pandemic season that everyone is muted upon entry. But of course, we do have chat and QA fields open, and I'll be keeping track of that along the way. As with many discussions, it's a lot easier if there's any sort of questions along the way. I know we'll have time for questions at the end as well, but given that this is a sizing focused discussion, I'm sure if you have topical questions, I'll keep an eye and I'll bring them up for our product expert, Michael, from the Zoeller team. In terms of a quick introduction, this is one of a series of webinars that we've been running for a few firms out in the Alberta and BC market, and starting to do in Ontario and East as well. But it's a wide range of more application focused discussions surrounding pumps, specifically submersible pumps available from Zoeller, rather than just here are the product details and here are the features and benefits. We really like to focus on the application focus here. So for those that may not know me, my name's Zach with ATS. I run our market development team and manage our national account program for firms that have multiple locations. And with me today is Michael Kelly from Zoeller, who's the what is the title? The product engineer, product guru, something like that?
Something along those lines. Application engineer.
Application engineer. So he's going to run through his sizing presentation today. If you would like a follow-up discussion specifically with your firm, feel free to shoot me a message at the end of the session or later on. Just Zach, Z-A-C-H, at atspec.com. And of course, we will have a follow-up email with some additional information. And the session's recorded. It will be up on our learning hub on the new atspec.com website. So without any further ado, I guess I'll pass it over to you, Michael, and let you take point.
Go ahead and share my screen, get everything set up here real quick. Okay, so I should be sharing my screen now. Hopefully you all can see that.
Yep, looks good.
As Zach mentioned, my name is Michael Kelly. I'm the application engineer for Zoeller Pump Company, or one of the application engineers now that we've hired a few more. I am a licensed engineer in the state of Kentucky, down here in the States. I've been with Zoeller now for a little over 4 years. My primary role with the company is to help contractors, reps, engineers, even down to the homeowner or the end user, troubleshooting more technical aspects of our product, or designing systems around our product, or offering our product as an alternative to maybe an existing design. Today, what I'm going to do is I'm going to present on pump sizing, or the basics of pump sizing. This would be considered maybe a 101 level course, but if you maybe have a more advanced question or any questions at all, as Zach mentioned, pop those into the Q&A chat or just the open chat, and he will bring those up to my attention either throughout or at the end, and we'll try to get all those questions answered. But after the introductions, we'll go ahead and get started. 1 second here. Okay, here we go. So the first question is why do we even use a pump? Now, if you're sitting in a presentation about pump sizing, you likely understand why pumps are used. It's generally an elevation concern. We've got water at a lower point, we need to move it up to a higher point. Although that's not always the case. Sometimes you'll notice applications where you probably could have put in a gravity system, but a pump was the better option. A lot of times it's a capital reason, capital cost. It's many times cheaper to put in a pumped system rather than a gravity system. Limiting site conditions can keep you from maintaining slope, or the excavation costs for a gravity sewer is very, very high. Whereas with pump systems, you can follow contour, relatively easy install compared to a gravity sewer. Other instances where it may be advantageous to use a pump is in flow equalization. So at wastewater treatment plants, or decentralized treatment plants, anywhere it's where the water needs to be controlled when and where it's sent, a pump gives us that ability. And that there at the bottom of the list, drip and other applications. A lot of effluent or on-site wastewater systems for the dispersal field, subsurface disposal of water, many times requires a pump to pressurize those fields to utilize that entire field. So at Zoeller, we manufacture 40, 50 different models of pumps, and within those models, there's multiple variations. So you have potentially hundreds of different options just at one manufacturer. And I understand there's probably other manufacturers that are vying for your business. So with the tremendous amount of options out there, how do you single it down to just one single pump? So that's what we're going to work on today. We're going to talk about the questions to ask. We're going to briefly discuss the various pump styles that we focus on at Zoeller. We kind of break that down into 3 or 4 different categories. We're going to talk about what a pump performance curve is, why it even matters to size a pump, and then we're going to kind of go through the fundamentals and an example of pump sizing at the end. So these next 2 slides are arguably the most important slides of today's presentation. That's the questions to ask, because for us to be able to size a pump, we need the information to size that pump. And these next 2 slides will ask the questions to get all of the relevant information that's needed. So the first question is, what are the electrical conditions? And when I ask this, what is the voltage and phase that's available at the site where the pump will be located? Is it 230 volt single phase? Is it 230 volt 3-phase? Is it 115 volt? Or, you know, you could be working on a larger project that's 460 volt. And the source power will actually be 240, 120, and so on. But the motors in each of our pumps are voltage and phase specific, and they need to be matched to the available service power. You can run a 230 volt motor on 208 volt power. The issue is it won't run for long. That's where we most commonly see the mix up. People assume that there's 240 volt power. They sell a 230 volt pump, and it ends up that they have 208 volt power. It will run, but it's going to prematurely fail. So we want to make sure that we're matching the available power to the pump that we're selecting. Also putting cord links. So cord links, I will say, is less critical, but it's my opinion that a no splice connection is the best connection. So the more that we can avoid cutting or splicing cords, you're going to have the best installation. If we can have a direct home run from the pump or the floats straight to the power source or control panel without ever having to splice them or use a junction box, that would be the best installation. Anytime you cut or splice a cord, it's a potential failure point. So again, home runs on all electrical connections are always best. Next question, is it residential, commercial, or municipal? This is so that we can begin to determine an appropriately economical solution. Sometimes we'll come up with this big grand design that we know will work based on the theory, and then it ends up being a $3,000 pump for a homeowner. They don't need a $3,000 pump. Generally, they need a pump that's a couple $100, maybe $1,000 at the most. So we want to make sure that we're value engineering this to some degree as well. Third question is, what are you pumping? So we primarily deal with wastewater pumps, and we characterize that wastewater into 3 different categories. The first one is sewage or raw wastewater. This is any water that will come from toilets, floor drains, garbage disposals, washing machines, dishwashers, any raw, unfiltered waste that could exist in just your traditional sewer systems. We have to deal with those solids that may be present as well. The other form is effluent. Effluent is typical to an on-site wastewater system, or also even on the municipal scale, they have effluent. At this point, most all the solids, fats, oils, and greases have been retained back into the treatment system, whether that's just a simple septic tank or an advanced treatment system like an aerobic unit, or even a municipal scale treatment system. there's just a few different there's no solids at this point, but there's a few other considerations that we need to keep in mind when we're selecting pumps for this application. The third one is groundwater, rainwater, stormwater, whatever you want to call it. It's mostly liquid, mostly clean liquid. It may have some silt or dirt that has washed in with that water, but for the most part is clean water free of solids. Now, continuing more into the more application-based questions. The first question is, what is your design flow? How much water can we anticipate to be spilling into this basin? Or how much water does this pump need to meet or exceed? That's going to be our minimum criteria when we're selecting a pump. We always need to select a pump that can meet or exceed the incoming flow. If we select a pump that cannot meet that incoming flow, we could have an overflow issue, which is a bad situation to be in. And what is your static head? So the static head is the vertical distance between the tank's water level and the outfall. We generally measure the lowest point in the system. So that's going to be usually the base of the pump basin or the off point of the pump. And then the outfall is going to be where this water ultimately dumps out into the sewer system, or out, if it's stormwater, it could be just pumping out over the hill or into a lake or a river, wherever the outfall of the pipe system is. How far are you pumping? So many times we'll refer to this as the horizontal run. This is the distance between the pump and the outfall. What diameter and type of pipe is being used? So are we pumping through 2-inch, 3-inch, or 4-inch pipe? Could be smaller, could be larger. Is this PVC pipe? Is this high density polyethylene? Is it steel pipe, or is it cast iron or ductile iron pipe? The different type of pipes can affect the friction loss. We need to know generally what type of pipe it is, and also the diameter as well. What fittings and how many do you have? So how many check valves, how many 45 elbows, how many 90-degree elbows? Are there any gate valves or anything else that would be an obstruction to the flow of the water? And the last question is probably the most commonly forgotten question, but one of the most important questions is, what are you pumping to? Are we pumping to a gravity sewer? Are we pumping to a septic system, or are we pumping to a pressurized system? So to kind of give just a brief overview of the different pump styles, we've really got 4 different categories that we break them down into at Zoeller. We've got sump pumps, which is going to be used for your dewatering applications in your basements or small commercial buildings. These are generally minimal solids handling because there shouldn't be a lot of solids outside of some silt or small debris that washes in with the water. There shouldn't be any solids in this application. These can be used in automatic or non-automatic orientation. And when I say automatic, I'm referring to a pump with a float switch already built into it. So you can see this pump here has kind of a float that will float up and down as the water rises and lowers to activate this pump on and off. You can see this one comes with just a standard plug. You can plug it into the wall and it will be able to turn itself on and off based on the demand of the application. That is an automatic pump. Sewage pumps, to be classified as a sewage pump, they generally have to handle a 2-inch solid or larger. So a 2-inch spherical solid needs to be able to pass through this pump free and clear of any obstructions. These can also be used in automatic or non-automatic. Grinder pumps are a derivative of sewage pumps, or solids handling pumps as we sometimes call them. But grinder pumps, rather than passing those solids whole and intact, as the name implies, it actually grinds those solids down into a fine slurry. That allows us to eliminate any sewer clogging material, such as wipes, feminine products, prophylactics, and allow those to pass more freely through the discharge of the pump and ultimately the sewer system that's receiving this wastewater. And these can be used in automatic or non-automatic as well. Effluent pumps are essentially the same thing as sump pumps. There shouldn't really be any solids in this environment because all that's been retained in the septic tank or the treatment system upstream of this. The one catch with effluent pumps is they should be used in non-automatic versions only. And the primary reason for that is the higher concentrations of hydrogen sulfide gas that exist in effluent applications. If the water level drops below the top of the pump, that will expose that cast iron pump to that hydrogen sulfide gas, which will corrode and cause a premature failure of that pump. If you use an external float switch, transducer, or something to set that off point above the top of the pump and keep it submerged at all times, it will prevent that pump from prematurely failing due to corrosion. Now, it's best practice to keep all of your pumps submerged at all times, but on a residential application, we use these automatic pumps quite often, where the off point is kind of somewhere here near the middle of the pump. On residential applications, it's fine to expose them some, but on commercial or municipal level systems, it's always best to keep your pumps fully submerged. Helps them run a little bit cooler and extends the life of the pump. So now moving on to what a pump performance curve is. So every pump model has a performance curve, and it shows its relationship between flow and total dynamic head. So a lot of people understand that a pump moves water, and they understand that flow rate is part of what that pump does. But many times the pressure or the total dynamic head is not always accounted for. If you were to walk into a plumber distributor or a wholesaler or your local supply store and you saw a pump on the shelf, that pump may advertise somewhere on the box that it can produce 30 gallons per minute. And in fact, it probably can produce 30 gallons per minute, but many times, or all the time, there's also another aspect, which is the pressure. So if we look at this pump curve here, this pump can produce 35 gallons per minute. You can see all the way out here at the end of its curve is about 35 gallons per minute. So it can produce 35 gallons per minute. And if I were to look at this pump on the shelf, it'll probably advertise itself as a pump that can do 35 gallons per minute. But it can only do that at a really low pressure. As the pressure increases, it's going to reduce its performance. And a pump will only operate along its curve. So it can also do 20 gallons per minute at 26 feet of head. It can do 30 gallons per minute at 15 feet of head. And another important aspect to note on pumps is what we refer to as the shutoff head, which is the maximum pressure that a pump can produce. And at that pressure, it produces zero flow. So this pump is somewhere around 31 feet. If you could imagine, if you were to have this pump sitting in a basin with a 40-foot tall pipe sticking straight up off the discharge, this pump will be able to fill that water or fill that pipe up to about 31 feet above the water level in the tank. And once it hits that point, that pump will continue to run, but no more water will be flowing out of the tank at that point. All pumps have their own unique performance curve. So we're going to start getting into some scenarios to talk about why sizing matters, why we need to go through this process. And the first one I'd like to talk about is horsepower, because it's always much more than horsepower. So even if that last slide was the first time you've ever been exposed to performance curve, anyone can look at this chart here and see that these are four clearly different curves. You have a very long, shallow curve here. This is one of our sewage pumps. So this curve tells me that this particular pump can produce about 390 gallons per minute, and it can produce a maximum pressure of about 35 feet. Alternatively, to the other extreme, this tall vertical curve here is one of our grinder pumps, and it can produce a maximum flow of roughly 45 gallons per minute and a maximum pressure of 105 feet. So one pump can do 390 gallons per minute versus one that can do 45 gallons per minute. And then these other pumps have different performances themselves. However, every pump on this chart is a 2 horsepower pump. So horsepower really has nothing to do with the performance of a pump. So if somebody's calling you and asking for a 2 horsepower pump, we need more information. We need to go back and ask the questions that we reviewed in those 2 slides earlier. What does affect pump performance, which we won't get into too much great detail, but to just kind of give you an idea, is impeller style, impeller size, motor speed, pump housing, design, solids capacity, discharge size. Now, if I increase my impeller style or maybe the impeller size, I may need a larger horsepower motor to drive that pump, but the horsepower itself does not have a significant impact on the design of the pump or the performance of that pump. So there is a balance when sizing a pump. Undersizing a pump can cause some of the issues that we've already talked about, which is overflow. That's where maybe we have 50 gallons per minute spilling into our basin. Our pump is only producing 30 gallons per minute. There's going to be a 20 gallon per minute excess. And over time, that basin's going to overfill, spill out into the floor, back up into the building, all of which are bad situations to be in. The second piece, which is particular to sewage applications, is we need to hit a minimum velocity to prevent clogging. So what velocity is to a pump system is what slope is to a gravity system. So for all gravity sewers, we need to maintain a proper slope. And that slope is designed to keep those solids in that sewer moving on further down the line, rather than stopping and piling up. In pump systems, we can't rely on gravity because usually we're going against gravity. So we use the velocity of that water to ensure that those solids resuspend and keep moving down the line. Now, when I say 2 feet per second, that is the absolute minimum for sewage applications. Generally, I recommend people to aim for a 3 to 5 feet per second. Too much velocity can begin to cause issues such as water hammer or erosion. Higher velocities will erode fittings and other pieces of the pipe over time. This is kind of a picture of what can happen if you don't maintain that minimum velocity. You can see this lower half of this pipe here has a darker material where the solids have actually begun to calcify. And as oils and greases or wipes flow through there, that calcified material can actually act as like a hook to grab onto that, ultimately lead to a clog. And on a pump system, it's rare to fully clog a pipe, but it will reduce the efficiency of that system. This one here is actually from a gravity application. They didn't maintain the proper slope, and this one actually did fully plug the pipe. You know, some people say, well, why don't I just put in a bigger pump? That can be problematic as well. Generally, larger pumps can lead to more issues such as short cycling, where we're turning the pump on and off in rapid succession. That will cause a premature failure of a pump due to overheating. Power consumption, larger pumps naturally are going to draw more power, more electrical power, and it's going to cost the owner more money on their electrical bill. On the residential scale, that's mostly negligible, but whenever you're talking about large pumps, tens or hundreds of horsepower, that on most municipal or large commercial applications, that could be a significant cost increase by going up to the next size. And the last one is cost. Generally, larger pumps are going to cost more money and could potentially price you out of the job or project. Now, I also like to talk about this. We refer to this as crossing over. When a customer calls in and says, I've got X manufacturer's pump, can you provide me a Zoeller equivalent or some other manufacturer's equivalent? If they're having repeated failures, that should always be a red flag. Repeated pump failures are rarely a pump issue and rather an application issue. So if they know they're having repeated failures and they're looking for something to solve that, we need to go back and ask the questions we talked about. Make sure that the pump that was selected was the proper pump. In most cases, it probably won't be. So what can we find or uncover to ensure that we select the proper pump? So always go back and ask the questions before you just simply cross over a pump. So we're going to get back to pump sizing. There's really only two things that we need to size a pump. We need flow, which is a volume per rate of time. This could be gallons per minute. If you're dealing with international customers, liters per hour. Many times for stormwater applications, engineers will specify cubic feet per second. All of these could be converted from one to the other. The second piece is pressure, or in or as we call it in this industry, total dynamic head. It's a measure of the back pressure from the system at a given flow. It changes with flow rate. More flow will increase friction loss, which will increase total dynamic head. Less flow will decrease it. So it does change with flow. Generally, we measure this in feet of water, and feet of water is just simply a measurement of pressure, a force per unit area. PSI, pounds per square inch, is another form of pressure, or pascals or kilopascals, again, if you're dealing with international customers. Total dynamic head is composed of 3 pieces. There's static head, friction head, and operating head. If you can determine your flow rate and your total dynamic head, both of those together provide what we call a design point. And with that design point, we can select a pump. So we'll just talk real quick about picking flow rates. Ideally, an appropriate flow rate for the project will be provided to you. Typically, if you're dealing with an engineer, they have some idea of what the flow rate needs to be. This can be from existing water usage. It could be from some method that they use to compute it. Very common in the sewage application, we use the fixture unit method for residential and small commercial applications. There's other methods that exist as well. Some rule of thumb ranges for flow in different applications. So for a residential sump basin with clay soil, clay is it's not very permeable, so it impedes the flow of water. So our pump will only need to produce maybe 20 to 25 gallons per minute to keep up. That same application, but with sandy soil, water flows more freely through a sandy soil, which allows, or means we need to pump more water. So about 40 to 45 gallons per minute. For residential effluent applications to a gravity drain field, you're looking at about 20 to 40 gallons per minute. Residential sewage basins, about 25 to 40 is typical. To kind of give a visual representation of total dynamic head, static head, again, is the vertical distance between the pump's off point and the outfall of the system. So it's just that vertical distance. Friction head is head loss in the system due to friction between the water, pipes, fitting, valve. So anytime 2 surfaces meet or are in contact of one another, there's a force between those 2 surfaces called friction. So as that water is moving through that pipe, it's creating friction, and that puts pressure back on the pump. The faster the water moves, the more friction loss there is. So more flow means more friction loss. Also, if we decrease our pipe size, we're going to increase our friction loss because we're reducing the cross-sectional area that water can flow through. Alternatively, increasing your diameter gives more area, which reduces your friction loss. You've also got friction, an increased amount of friction when you're pumping through fittings, valves, and other obstructive fittings as well. The last piece is operating head. So this is any required pressure at the end of the system, many times referred to as distal pressure or force main pressure. So low pressure sewer is becoming more and more common. So if you're tying into a pressurized system, we need to know what the pressure is on that main before we can tie into it, because that pressure is ultimately going to push back against our pump. So we need to not only be able to have enough pressure from our pump to make it to the force main, but also to exceed that pressure on the main so that we make sure we're actually getting water forcing it into that pressure main. If you could calculate each one of these individually or determine each one individually, just add those 3 together and you get your total dynamic head. Not all systems have operating head. If you're pumping to a gravity sewer or just kind of out to the atmosphere, like for stormwater applications, many times we'll just pump out over the hill, or we're pumping to a river or a lake or a stream. Those types of applications don't generally have any sort of operating head. It's where we actually have a pressure requirement at the end of the system that will have operating head.
So I'll just a quick pause here, Michael. A couple of questions coming in from the chat. I think a lot of them mainly in the sense that you're giving it a lot of great information and they're looking to retain it after. So a number of people looking for, copy the slides. And I'll just mention, we will have a recording of the session, as we mentioned, available on the ATS Learning Hub. and we'll likely host a copy of the slides there as well, so that you could download those after the fact. We do have some of the information in here as some cheat sheets as well. So as part of your follow-up, you'll see likely a note coming from myself to those that attended. And if you don't, feel free to reach out to me and we'll get some of those cheat sheets passed around to you as well. But I think a lot of great content so far, good information that you're sharing. So just figured I'd jump in and give you a second to drink as well.
I appreciate that. So we'll get back into friction loss and the variables that affect friction loss. The first one is that it varies with length and diameter of the pipe and flow. So I've already talked about the diameter a little bit. Smaller diameter, more friction loss, larger diameter, less friction loss. The length is also a factor. So the longer the pipe is, the more contact time you have between the water and the walls of the pipe. So your friction loss is going to increase with an increase in length. In order to calculate what our friction loss is, we need 4 pieces to determine the friction head at a given flow. So we need the type of pipe, the length of pipe, the nominal length of pipe, what that horizontal distance is that we talked about before, the diameter of the pipe, and then the equivalent length of fittings. So we'll talk real quick about the equivalent length of fittings. So what do we mean when we say equivalent length of fittings? When we're calculating friction loss, we need to not only know the friction loss through the pipe, but we need to determine the friction loss through each individual fitting. Calculating the friction loss through each individual fitting can become quite cumbersome because you have multiple variables at that point. So to help reduce the amount of figuring that needs to be done, we're going to convert all of our fittings to an equivalent length of straight pipe. And what that tells us is we have our various fittings down the left column, or we'll use this chart here, which has our various fittings down the left column, and our pipe diameters across the top row. And what this chart tells us is how much one fitting, or what the friction loss through it is through one fitting, is equivalent to the same amount of straight pipe. So for example, if we have a 1 1/4 inch check valve, the amount of friction loss through that single valve is the same amount of friction loss through 11.5 feet of straight 1 1/4 inch pipe. So if we can determine the equivalent length for all of our fittings, we can reduce that down to one single variable, which is length of pipe. So once you have your equivalent length of fittings, you add that to your nominal length of pipe, which is that horizontal distance, how far we're pumping, and that gives us our total equivalent length. And we'll run through this in an example here in a minute that will kind of make more sense of this. This is probably the most confusing aspect, I feel, of pump sizing. After we've determined equivalent length, we need to come up with what we call our friction factor, which our friction factor is how much friction loss we have for every 100 feet of pipe. So down the left column here, we have various flow rates. And this particular sheet will actually extend down further with additional flow rates for higher flow applications, but it's been cut off for clarity here. Across the top row, you've got your various pipe diameters again. And under each diameter pipe, you have 2 columns. You have a loss column and a velocity column. So the loss column will give us our friction loss for every 100 feet of pipe. The velocity column will give us the velocity of that water at that flow rate and that given pipe diameter. So for example, if we had 25 gallons per minute flowing through a 1 1/4 inch pipe, our friction loss would be 7.89. And again, that's 7.89 feet of friction loss for every 100 feet of pipe. Our velocity, which is always good to check in sewage applications, is 5.36. So we're above that 2 feet per second minimum. You also notice on this chart, there's kind of like a darker gray area for each diameter pipe. That darker gray area is kind of where you want to be. It starts at a minimum of 2 feet per second, and it goes up to a maximum of about 8 feet per second. Again, I talked about earlier how too much velocity can be problematic. So you kind of want to stay between 2 and 8 feet per second. Now, if you go above 8 feet per second, Do you need to go back and completely redesign the system? No, not necessarily. But you want to try, if you do have some control over the pipe size that's being used, to try and be in this 2 to 8 feet per second range. So this is kind of the equation of that. Once you determine your friction factor, the H sub F value here is what we found on that previous chart. You'll take your total length, divide it by 100, and multiply it by that factor. So for example, for a 50-foot pipe, you'll take that 7.89 value and multiply it by 50 divided by 100, or it's 1/2 of that friction value. For 200 feet of pipe, you'll simply multiply it by 2, because 200 divided by 100 is 2. And once your friction head is calculated, you just add your static head and you're done. Now, this is, of course, assuming we don't have any operating head. I forgot to put the operating head here, but if you're pumping to a gravity system, your operating head will always be 0. You then have your design point, you can pick a pump.
So just on that point, before we get to the design point, for that length of pipe and also for the equivalent lengths when we're looking at fittings, do those values change based on the material? So HDPE or cast iron? That was one of the questions that came in from the chat.
The fittings conversion, not so much. It really depends. You can find slight variances on this depending on where you're looking. Most plumbing codes will have these charts for you. It can change. Usually it's generally ductile iron pipe or plastic pipe. Usually the difference between PVC versus high density polyethylene is pretty minimal. Where it can change, and we'll talk about this later, I didn't mention it before, but your friction charts do change based on your pipe material. So plastic pipe, it comes down to what we call the C value, which is the roughness coefficient. Plastic and high density polyethylene pipe and PVC pipe, they generally have a C value of 140 to 150, whereas ductile iron pipe or cast iron pipe can be much less, as low as 100. And that will affect the friction loss per 100 feet of pipe. So whenever you're looking at these friction charts, make sure it's applicable to the type of pipe that you're using. And this one here doesn't say, but this is for PVC Schedule 40. And in the example that we show later, it actually calls out PVC Schedule 40. So on the fittings and the total lengths, it may have a slight impact, but where your greatest impact is going to be on your friction charts. You need to make sure that your friction chart is appropriate to the type of pipe that you're using.
Perfect. Thank you.
Let's see if we can get back to where we were. Okay. So once we've calculated our static head, our friction head, and then we've determined whether or not we have any operating head conditions or not, we can then plot our design point. So kind of with a quick example that we've been going through, if our flow rate is 25 gallons per minute, our static head was 10 feet, our friction head was 8.9 feet, just assuming we don't have operating head, our total dynamic head would be 18.9 feet. So to plot that, you just find on your horizontal axis, you have your flow rate, which is 25 gallons per minute. Our vertical axis is total dynamic head, or our feet of water and pressure, which is roughly 19 in this case. We'll trace those two together, and that is our design point. With that design point, we can select a pump. So we looked at performance curves earlier, what they are. So this maroon or reddish curve here, it can produce 25 gallons per minute. You can see the performance curve goes beyond the 25 gallon per minute mark. The issue is it cannot produce 25 gallons per minute at 19 feet of head. So any curve that passes to the left or below our design point can be eliminated. Then generally which pump passes over or directly through the design point are the ones that you want to use. And to go beyond that, whichever one is usually closest is the best solution, because this one will most closely match what we need. So this orange curve would be most appropriate. Now, can you use this purple curve? Yes, you could. Right now, we're in unique times where lead times are longer than they've ever been, and getting particular product can sometimes be difficult. So if I can't get this orange pump for a few weeks, but I can get this purple curve same or next day, then this one would probably be perfectly fine for my application. Rather than producing, 25 to 27 gallons per minute, this one might produce 30 or 32, 33 gallons per minute, which isn't an excessive amount and shouldn't cause any issues. So we'll run through an example real quick. A contractor's asked you to specify a pump for a small commercial building. They have given you the following information. Design flow is 35 gallons per minute. They have 300 feet of 1.5 inch Schedule 40 pipe, 1 check valve, 1 gate valve, 4 90-degree elbows, 10 feet of vertical rise, 2 30-volt single-phase power, where they need 2 30-volt single-phase motors. Now, it's very, very unlikely that you'll ever get all this information on your first phone call or your first email. So that's why it's good to keep these questions either at your desk or in a document that you can send to your customers, and they can fill out that information for you. So if you ask all these questions, you'll get all the information that was given in the previous slide. So first things first is to determine our equivalent length of fitting. So we were told that we had 1.5 inch check valve, 4 90-degree elbows, and 1.5 inch gate valve. So we'll use our chart down here to determine those equivalent lengths. So for an 1.5 inch check valve, I've got my 1.5 inch diameter. I'll go down to the check valve row, and it's 13.4. So 1 check valve at 13.4 feet each, 13.4 feet each is a total of 13.4 feet. We have 4 90-degree elbows. So again, 1.5 inch diameter. Each 90-degree elbow is equivalent to 4 feet of straight pipe. So 4 times 4 is 16. So our total equivalent length in 90-degree elbows is 16. For the gate valve, we had just one of those. So we'll find that from our chart, and that value is 1.1. So we'll add up these totals, 13.4 for our check valve, 16 for our 90-degree elbows, and 1.1 for our gate valve, gives us a total equivalent length of fittings of 30.5 feet. You will then add this to the horizontal run when computing your friction head. So the next piece we need is the friction factor. So again, the pipe material is Schedule 40 PVC. So we want to select a friction chart that is representative of the pipe that we're using. So for Schedule 40 plastic pipe, this is the chart to use. So I didn't have this on that previous slide, but this is also very important to understand. The required flow is 35 gallons per minute, so we'll find our flow rate there in the left column. We're using 1.5 inch pipe. So we'll trace down that loss column and we get the value 6.95. So our friction factor is 6.95. Also, since we're pumping sewage, we want to check our velocity, which is 5.51 feet per second. So we're above that 2 feet per second minimum, but we're not producing an excessive amount of friction loss, or velocity rather. So our total length is 300 feet. That was the horizontal distance between our pump and the outfall. We had 31 feet of equivalent fittings. So we add those two together, and our total length that we're going to use to calculate our friction loss is 331. Our friction factor based on 35 gallons per minute and 1.5 inch pipe was 6.95. So if we plug those two values into this equation, we get 331 divided by 100 times 6.95 gives us 23 feet. So our total friction loss for this application is 23 feet. Now we could calculate the total dynamic head, which again is the static head, the friction head, and the operating head. The static head was given to us at 10 feet. That's a field measurement. We have to rely on someone in the field to provide that for us. So that was just given to us at 10 feet. Our friction head we calculated to be 23 feet. They mentioned that they were pumping to a gravity sewer. So since we're pumping to a gravity system, the operating head is 0. And the total dynamic head, therefore, is 33 feet. So now we can select a pump. Our design point is 35 gallons per minute, 33 feet of total dynamic head. Again, we find our flow rate on the horizontal axis, 35. Our pressures on the vertical axis, which is roughly 33 feet here. We trace those two together. And again, the X model pump can produce 35 gallons per minute. You can see this curve reaches all the way out here to about 42 or 43 gallons per minute. However, it can't produce 35 gallons per minute at 33 feet. So we can eliminate the X from being considered. The Y in this case would be the best solution because it can produce 35 gallons per minute at 33 feet. Now, again, the Z model pump would probably work if for whatever reason we couldn't get the Y pump for an extended period of time. But without any additional information, the Y pump in this case would be the best solution. So that wraps up my presentation. We'll open it up here a little bit for any questions.
So we have a few that actually came in there, and one might be good to jump back to that last slide with the curve and the 3 different pumps.
Okay.
They had a question on the curve steepness, and whether, obviously the 2 pumps that are right at the design point here are both relatively similar in how steep they are. But if you had 2 that were in that midpoint, one was flatter and one was more steep, how would that affect your choice?
Okay, I think I understand. So if a pump curve, we'll just use this Y here, if it were to extend out this way versus dropping off sharply. Really, versus one that drops off steep versus one that continues out, it's really hard to say. Usually the best thing to do is keep it towards the center of the curve. So we'll go back to where, let me see. Oh, I'm in the wrong.
Yeah, I think that the center of the curve really does kind of tie into one of the questions here. In looking at that, if you're more on the steep side versus more on the rounded edge or more in the middle, is there a place on that curve that they should be looking for?
So generally the ones with the steep drop off are generally going to be your grinder pumps. That's usually where you see that steep drop off, and that's usually due to an inlet restriction. It's just the maximum amount of water that can come in. Your solids handling effluent pumps are going to have kind of this longer continuous curve, I guess you could call it, where it doesn't have that steep drop off. Generally, you want to keep your operating point towards the center of the curve. Now, versus one with a steep drop off versus one that continues, it's really going to be about the same. Many times that the one that continues may be a larger motor, so that may be reason to stick with this one. Your amp draw increases as you move further right. So if you've got one that, if you're comparing 2 different curves that meet the design point, again, pick one that's closest to the center. Because the closer you are to the center, the closer you are to what's called the best efficiency point. Now, if you're operating down here at the end, you're getting more work or more output from the system. You're getting more flow, but you're doing it at the cost of running at higher amps and potentially overheating this pump. Now, for these ones that drop off, this is something that's not necessarily commonly known. Your highest amp draw is actually here in what I would call the knee of the curve. Now, when I say that, I don't want you to be concerned about operating here, because though that is where the highest amp draw will be pulled by the motor, if you're operating anywhere on a published curve, you're generally safe. Where we get concerned is if you're operating beyond the end of a curve, say this yellowish curve here. A pump's performance curve will actually continue down into negative pressures. The issue is that as you get further out here, you're going to be pulling more amps than what that motor is rated for. So these curves are actually cut off at a specific point, because beyond that, you're going to be overloading the motor. So as long as you can routinely stay on the curve, you're going to be okay. But as far as comparing the two, whatever's closest to the center of that performance curve would probably be preferred. Hopefully that answers the question.
Yeah, I think that clears it up pretty well. So a couple of quick ones that I can answer as I open it. First, there was a question on, that complimented your presentation, said you gave a lot of great points, and they were wondering whether or not there was a similar cheat sheet or guide for basin sizing. And the answer is yes, we do have a full other basin presentation, and based on the feedback here, maybe we end up setting that for a month, a little bit down the line. We can get another ATS Learning Hub session on that. Or if you'd like to shoot me a note at zach@atsspec.com, we can get that set up specific for your office. Another one that came in regarding an elevator sump pump where they have hydraulic oil and they're looking for an alarm assembly that will prevent pumping out, and perfect flow in there because there's the oil guard assembly from the Zoeller product line. And certainly we can help you size and select all those with the controls. Shoot me a note and we'll get that over. A couple more more specific ones coming in here for you, Michael. Other than high velocity, what can cause water hammer in sumps? Is that something that's come up for you before?
Yes, so water hammer there's really two components. The first one is velocity. The second one is the rate at which that velocity changes, because water hammer occurs when there's a great change in momentum. So there's two pieces, there's mass and velocity. So there's the mass of the water, which we can't really control. Whatever volume is in that pipe is the volume that's in that pipe. The second piece is velocity. So whenever we stop that water at a very fast rate, there's an instantaneous change in that momentum. And that's what causes that jarring effect that we can hear audibly as water hammer, and it could cause tremendous damage. In extreme cases, it can blow apart fittings or burst pipe. The one thing that generally in sump systems where you have water hammer is the reversal of water back through the pump. So the pump will be running, it will be sending water up out of the pit. The pump shuts off, and all of a sudden that water reverses direction. It's coming back through the pump before that check valve can close. Then all of a sudden that check valve slams shut, stops that flow of water and creates water hammer. So we have, they're called silent checks, I believe is our marketing term for them. And it's a spring assisted check valve. And what that does is it closes that check valve instantly. It's always got a little bit of pressure pushing on that check valve to close it. So that way, when the pump shuts off, that check valve closes immediately before the flow of water can reverse in direction. So if we can close that valve before that flow reversal happens, then we can avoid water hammer. So for your typical sump system, that's what we would use.
Perfect.
Now,
go ahead.
One quick caveat that I want to throw in there. I don't want to get you confused and think that quick closing valves are what prevent water hammer. That only prevents it on the check valve in the sump to prevent flow reversal. Down the line, it's going to have the exact opposite effect, because if you close a valve rather quickly, like a ball valve, or maybe there's some actuated valve, if it closes instantaneously, that's going to cause an instant change in momentum. While your pump is still, let's say your pump is running and you instantly close a valve, that's going to cause water hammer. The best way to control that is either shut the pump off before you close that valve or slowly close that valve to give it a gradual change in momentum rather than an instantaneous change in momentum. So kind of two different things. The quick closing valve on the check valve helps prevent the flow reversal. So that's why we use a quick closing valve there.
Perfect. And then maybe good to go back to one of those early slides where you had the breakdown of application and types of pump, because there's a few different questions on like effluent pumps and auto versus non-auto again. So if we could maybe reiterate that and what's recommended for a storm sump. Specifically, if you could elaborate, where did it go? Yeah, should the effluent pump be an auto or non-auto? And if you can just maybe reiterate the automatic versus non-automatic.
Okay, so whenever we talk about automatic, it has a float switch generally built into the side. Sometimes these can be a tethered float that comes out of the cap rather than sitting on this rod here or this guide. But the issue with these is that the off point is going to be below the top of the pump. So this off point for this particular pump is going to be kind of right here at this seam between the motor housing and the pump housing. That's fine for most of your residential applications, for sewage and sump or dewatering applications. For effluent applications, you want to use non-automatic pumps where you will have to use an external float switch or transducer with an off point above the top of the pump. We do that to keep these pumps fully submerged and protected from the hydrogen sulfide gas, because there's hydrogen sulfide gas in really any sewer system, but effluent systems, it's at a much higher concentration. So to the point where it can actually begin to corrode this cast iron and the seals between the cap and the motor housing, or the seals between the motor housing and the pump housing. So we want to keep these pumps fully submerged. For commercial or large municipal stormwater or large commercial stormwater applications, or even sewage applications, I generally recommend non-automatic pumps for those larger applications, because we want to keep the pumps fully submerged to help them run cooler. So in larger, more demanding applications, we want to keep those pumps running as cool as possible. In residential applications, it's usually pretty rare that these pumps should overheat, unless they're being short cycled. That's a different problem than just being exposed to air.
Okay.
Hopefully that answers the question.
Yeah, thank you. And then a couple kind of general applications, which probably a little bit more unique for north of the border here, but if they're using a pump for duty standby application, is there anything special that needs to be considered? And similarly, if they're using a lead lag application, is there a different set of factors that need to be considered?
So by standby, there's duplex and then there's two pump systems. I think by standby, I imagine they mean that they have a pump that's just there only in high water conditions. That is never to really be used except for in extreme conditions, maybe.
Yeah, I think that would be it.
I generally don't prefer standby. I prefer duplex that alternate pumps. The issue with standby pumps is that if they never get exercised or used, the seals on them can actually dry up or dry out and fail prematurely. It's usually the issue we see with those, because if they just sit for an extended period of time, they can actually gum up and stick together. Whenever that pump kicks on, it can break that seal, and then eventually that pump will fail prematurely. So that's usually why I'm not a huge fan of standby pumps, unless it's like a large commercial application and you have advanced controllers. We have what are called exercise timers, where we'll actually turn that pump every month for a couple minutes, to where it'll actually just run that pump to make sure that those seals are moving, everything's moving. The alternative is just a duplex alternating system, where I believe you're talking about lead lag. Usually those are sized for 100% redundancy, so a single pump can keep up with the demands of the project. The advantage of the alternating is that you essentially are only running each pump half the time of what it normally would be. You've also got that redundancy. One thing that I like to keep in mind on those is to put your alarm float either with the lag, combine the two into a single float, where you have your lag and your alarm activated at the same time, or put your alarm float before your lag float. The issue, if you do it in the traditional sense, where you've got your off float, your lead float, your lag float, then your alarm float, you'll never be notified of a failed pump. If your lag pump can keep up with the demand, you'll never hit an alarm and know that your first pump has failed. You won't get an alarm until both pumps have failed. Then you've lost that redundancy at that point. So always combine the lag and the alarm is my preferred way of setting up those floats. Hopefully that answered the question too.
And would you recommend separate floats and control and not integral to the pump?
For residential applications that have duplex, the alternator is not a bad idea. And those would be used with automatic pumps. That's just a box that plugs into the outlet, then you plug each pump into the side of it. That's okay for those residential or light commercial. Generally for larger commercial or municipal, I always recommend external floats or transducers to activate those pumps.
Perfect. All right. Would you mind just stopping sharing screen for a second, and I'll take over as we finish up here?
There you go.
Thank you. So first and foremost, I see we're getting to the end of the time here. So I do want to say a quick thank you to all those that joined us today. I understand if you may need to jump off real quick. I did want to show you where you can find the products that we talked about today on the atsspec.com website. So you may have noticed that if you were familiar with our old systems, we have a new landing page at the atsspec.com website. And of course, if you're looking for this information after the fact and you go to the architects and engineers, you'll see a learning hub here where we have our training on demand, all the videos and recordings that we've done, as well as our knowledge base with has blogs and cheat sheets and things like that. And you can log in through the button here. If it's your first time, you can book a demo to get a personalized walkthrough of the system with our market development team. I wanted to jump over. I've already logged in and made a project here. You can see we have Zoeller webinar demo, and this is me looking at the specs that I've added so far. Once you've set up your project, it's very simple to add a new product. If you've already gone in, maybe gone back and forth with Michael or any of the other application engineers down south, you can hit the plus button. And then there's a number of different ways that you can find product within this site. You can search by product model number. So BA 161 would pull up the pump. You could search by series if I want to search for a Shark, which is one of the grinder pump options. And of course, you can search my personal favorite. I like to just get into the category so I can search for pump, or if you have any of the other specific options. So like the question came in the chat for the elevators, there's the oil guard assemblies, but we can jump into the pump category here. And once we're into the category, there's an even more refined search option here. You can see there's a number of filters on the left as well. So for example, we mentioned grinder. You can select the grinder option and it will pull up all the different grinder pumps available. I'm just gonna select one of the ones here to move us along because I do want to respect everyone's time. The nice aspect of the ATS spec website, and the reason that Zoeller partnered with ATS, is that it's not just the base cut sheet model. What you get is a configured product. So all the various options that are available for a product are shown here, and you can go through and make your selections. We mentioned the cord length. So as Michael mentioned, you may want to choose the exact cord length to make sure you're getting a single connection. And you can see in the bottom, this add to drawing button went from gray to blue because it's now acceptable and all the selections necessary have been made. If you want to view the additional details, that view spec sheet button will pull up the Zoeller and any of our manufacturers' actual spec sheets. And you can go in, review the design flow curves like Michael pointed out, the handy dandy charts as well, all the different voltages, get our amps and everything else that we need. But we'll hit add to drawing for now. The part that ATS does behind the scenes is, correlate products with other products that work. So for example, we're going to get our the recommended control panel popping up here. So this is the 1168 control panel, which is the one that's tied to this pumps, and the data and rule engine is built into our system. So I'll hit add to drawing again, and it's going to add that in. I can then hit complete if I'm done with my selection, or there'll be a add another drawing or add another product to your project file. I'm going to hit complete for now. And you can see I've got SP1, SP2, and now our SP3. Of course, you can add in notes if there's any approved alternates, other notes that you need to make, maybe on float trees or anything like that. Or you can go up to this download button, and the next best thing that Zoeller partnered with ATS for is that configured product is actually included in the output spec. So again, not just a generic cut sheet that's non-selected. It'll give you the specific model that you've selected for your project. So I've already downloaded a handful of these ahead of time because I had a feeling we might be running long, but we do have our ATS submittals, which is a marked off version of a PDF product. We have a fixture schedule in Excel, and this will print off with different schedules and different columns based on the product type that we're looking at. Various written specs in long and short, as well as a CSI spec here on the right. You can download the Revit for the entire project or those specific manufacturer cut sheets as well. So I'll download a schedule here, and you can see it's going to put together the information, and it'll go from gray to blue once again. Again, for now, I am going to pop over to the manufacturer cut sheet version that I pre-downloaded. So it gives you a nice title page, shows you the model that's been selected, and of course those specific detailed cut sheets like we talked about. This is the submittal format, nice title page. You can have a customized logo here on the front, so it outputs as it's coming from your firm. And the options that we select are always marked off as well. You can pop over to a couple of written specs. So if you were working in a CSI 3-part written spec, you can simply copy and paste from these product selections into your overall written output spec. Similarly, if you have a different format that's maybe a little bit more organized differently, you can get the same information just organized in a long or short spec version. And then, as I mentioned, we'll download our fixture schedule, pop that open. And once again, just like everything else, open and editable. So you can see we do have the pump schedule specific. It calls out our deadhead, calls it the max flow, all the other details that you may need. Simply copy, paste, and you can pop that into your drawings. So what we've done is try to simplify the way that you can take the information from the manufacturer's spec sheet and get the information you need to put into your written documents or your CAD, your design drawings, PDF floor plans, whatever it is. However you're going out with this information to market, we should be able to provide you the information that you need. So that's the very quick version. If you'd like a more detailed overview, I'll be happy to jump in and do that another day. For now, I just want to say a quick thank you for joining us today. Obviously there's a lot of great questions there, a lot of great feedback. So Michael, you must have done a fantastic job. There was a lively audience today. So appreciate you spending your time with us. Thank you, Michael, for all the detailed information. Of course, we'll be sure to follow up with anyone that had reached out with the more detailed questions that we said we get back to you after the fact. We'll certainly do so. Again, if there's more questions and more detail you'd like, we can steal more of Michael's times and have a firm specific version of this for you. And I guess keep a lookout for the basin sizing in the future because there's already a couple of questions on that coming in.
Perfect. Thank you all. And thank you, Zach, for putting it on.
Perfect. Well, enjoy the rest of your day. Have a great rest of the week, and we'll talk to you soon. Bye for now.